question?
Good afternoon. I'm Watanabe. Or I'd better say my first name, Masaru. I'd like to talk about the state of the surface hydrogen and the reaction condition of heterotrophic synthesis. This is experiment performed by Professor Peter Biss and then University and myself. First of all, I would like to propose a simple question. That we often introduce hydrogen gas onto the air catalyst, for instance, at about 400 C. According to the summer dissolution experiment, the absorbed hydrogen is unstable, and most of the hydrogen is dissolved. Under such a condition, we introduce the hydrogen onto the catalyst surface. However, we can obtain a nice Fischer-Tropsch reaction without absorbed hydrogen. No, I don't think so. There are some absorbed hydrogen on the surface. Such a state of hydrogen might be much different from the state obtained by the low temperature with the high vacuum condition. That's my point why we perform such an experiment in ipsometry. Now, the ipsometry is an optical method which has no interference from the ambient gas phase. This is very advantageous, but there are some disadvantages which become clear by my talk. Now, we made two kinds of the ellipsometry experiment. One is the manual type or static observation of the absorption effect observed by manual type ellipsometer, which is given by or shown by the upper part of the slide. And the lower part, we use the evaporated thin film of the ion, the cell, and shown over there. And at the same time, we could observe the electrical resistance. Thank you. Electric resistance of the film, which is influenced strongly by the absorption of hydrogen. And as well, we could observe the change in the work function and the heat of absorption. Next slide, please. Now, this is the Raman ellipsometry combined system by which we observe the very quick, we could follow very quick chemical reaction of the surface. And tomorrow in the morning session, I will talk about some result of the Raman's catalyst of the surface graphite. But here, I focus only on the rapid reaction of hydrogen on iron surface. Next slide, please. At first, I have to talk about the principle of the rotating analyzer ellipsometer. That light intensity reflected from the surface of the catalyst, which is modulated by the rotating analyzer. The light intensity is given by the fact that this equation, which consists of the cosine part and sine part and the constant. Each coefficient, K0, K1, K2, calculated or observed according to these equations. By those coefficients, we can calculate the ellipsometric parameter delta and C. Delta and C is defined by this equation here. Amplitude reflectance of P polarized light to the ratio of the reflectance of S polarized light is equated in terms of the amplitude ratio C and the phase difference delta. Those two are kind of the optical constants. Those two quantities are directly converted to the direct constant, complex direct constant, the real part, the imaginary part of the direct constant that determined from the C and delta. Next slide, please. Now, this is the one example of the rotating analyzer intensity of light, the function and rotation function alpha, to perform the one rotation, it takes about 75 milliseconds. So that we basically we can follow very rapid surface reaction by using rotating analyzed ellipsoid. However, our case, we accumulated 13 times the rotation for 1 second. By this method, we can evaluate very precisely the change in the delta delta-c. This is somewhat important and resulting in what probability in such an average of the rotations. The next slide, please. Chemical reaction of the surface or absorption of some gases may cause change in the delta delta-c. Those we defined by those two equations. In what follows, we analyze the delta and delta-c according to classical layer models. This is reasonable for the thick surface layers. However, in the case of the absorption, the layer thickness is so thin that such a classical model becomes unreasonable. So our conclusion from such a model calculation might be somewhat qualitative, not to be so quantitative. Next slide, please. Now, I start with the static observation by using the manual type ellipsometer. Here, the changing the ellipsometry parameter delta and delta-c plotted against the absorbed amount here. And in figure A, effect of hydrogen, absorption of hydrogen on iron, and B, you may find the reaction. Sorry. We try to compare the effect of absorption on iron and those on palladium. Here I show the ellipsoid parameters as well as the heat of absorption Q and change change in the electron resistance film and the change the work function. You may find there are some similarities. Basically, both effects are the same. And this is the effect of the 0 degree C. The next slide will show you the effect of the absorption of hydrogen at the liquid nitrogen temperature, A for the iron film and B on the palladium film. In the case of palladium, it's well known at the low liquid nitrogen temperature, the hydride is formed, so that at high coverage above the monolayer amount of the monolayer absorption, we observe very large change in the delta and delta-c, which is evidence for the formation of hydride. Now, in this slide and the previous slide, I want to note or emphasize that delta is always positive. This is the evidence of the absorbed layer. Some layer is formed on the metal surface. However, if absorption of hydrogen, for instance, takes place, then the negative delta is expected. This is most important part, which will be emphasized in the following couple of 3 or 4 slides. Next slide, please. Now, I go to the main issue, which was observed by the rotating analyzed ellipse. Here, in figure A, I show you the absorption of hydrogen at room temperature. Here, at the time 0, the computer starts the observation, and then I start to I start to rotate the bar, liquid bar, I start to open the valve to introduce hydrogen gas into the around the 12 second, hydrogen starts to dose, and around about 20 second, 100 toll of the hydrogen pressure is attained, and the steady state is also attained after this time. Here we observe the positive delta delta and small negative delta delta, which is consistent, which those two effects are consistent with the result in the previous slide. So that at room temperature, there exists clearly some type of the adsorbed layer, which consists of perhaps the H minus, H plus, and molecular hydrogen. Now we go to the experiment at high temperature. Here, at high temperature, 400 degrees C, we observe very different behavior of the delta C. As I told you, positive delta means something adsorbed layer. However, at 400 degrees C, and also at 500 degrees C, we observe always negative delta, which may signify that there is no adsorbed layer, but there might be some hydrogen, perhaps under the surface, I think. But here we have a very rapid drop in the delta and the recovery of delta. This is very unexpected. We can't explain well this result or this effect, but I believe at this stage, some formation of the dissolved layer occurs. However, such a dissolved layer is perhaps unstable, and after some time, such a dissolved layer disappears, and here we have a subsurface hydrogen. Now, the same effect is observed at 500 degrees C. Here, we introduce the hydrogen gas of 320 toll. So the pressure is a little higher than the previous case. So here also we have a large drop and recovery of the delta, and we have the subsurface hydrogen. However, the temperature high, the parts of those negative change in the delta and delta C are caused by the diffusion of hydrogen into the interior of the lattice. Next slide. So such a behavior might be somewhat specific to the iron side. So I want to demonstrate the case of the hydrogen absorption of hydrogen on cobalt surface at 400 degrees C. This case effect is somewhat different, but basically to say, in stage A, we have a subsurface hydrogen, because always in this case also the delta is negative, which means perhaps no adsorbed layer. But the sudden drop up of the delta, this is also very drastic effect. We can't well understand, but in this case, there might be some hydride-like layer. According to our layer model analysis, at stage A, we have a dissolved layer whose thickness might be 9.5 angstrom, and at stage B, we have a dissolved hydrogen layer as well as the hydride-like layer on the dissolved layer. Next slide. So far, we obtained the hydrogen at high temperature very different from the state at low temperature, at the room temperature or at low temperature. So what kind of the effect or role of the dissolved layer can be expected? Such point might be investigated in the next step. Here, we investigate the Woodard reaction on the iron surface at 400 degrees C. Here, I introduce a carbon monoxide at around the 11 second, and then the 100 toll of the CO is introduced, and the steady the accumulation of a carbon layer on the iron surface. So with using such a carbon layer, we introduce again the hydrogen onto the carbon-covered iron surface. Here we obtain a very rapid and drastic decrease in the delta. This means elimination of a carbon layer with forming hydrocarbons. So those two are very consistent. Here, accumulation of something, in this case the carbon layers, with a positive delta Z, large positive delta Z. And here we have a large negative delta delta. This means elimination of a surface layer. The next slide, please. And to confirm the result shown in preceding film, I show you another example. Here I produce a carbon layer which is emerged from the inside of the iron during the heat treatment procedure. Perhaps we have such a curve above the surface. We have a defective graphite, and just the contact of the iron metal, we may have the carbide carbon. In this state, we can observe the Raman band of the defective graphite at 1358 Kelvin. With using this graphite, using this sample, we introduce hydrogen at 400 degrees C. Here we observe again the drop in the delta and a small change in the delta C. We believe at this stage there occurs some surface hydrogen, and at the stage 2, perhaps the accumulation of a carbon complex takes place, and then production of the hydrocarbon followed, and we observe that decrease in the delta. So this some of the complex curves can be well understood. Next slide, please. Now, we have to rationalize. At high temperature, we have almost no absorbed hydrogen. But we have some hydrogen under the surface. This is my proposal. So to rationalize such a state, we have two aspects. At first, we have to consider the state of hydrogen. State of hydrogen can be assumed to be atomic, weakly absorbed, and mobile state of the state, described by the two-dimensional figures, or described by the two-dimensional van der Waals equation. Skipping over the subderivation equations, we can obtain, this is a very elementary equation, perhaps you may remember easily, the chemical potential of the absorbed hydrogen in the two-dimensional figures. We obtain this equation. Here I want to emphasize that the coverage theta appears in this form and this form. In the Laminar isotherm case, of course, we obtain only this part. So with increasing the coverage, the chemical potential of absorbed hydrogen becomes rapidly high. That means the coverage might be always small. Now the next effect is, of course, the equilibration with the gas phase. Of course, high-speed H2 molecule may collide on the surface. This has a strong effect. With the equilibrium condition, of course, we obtain a well-known result here. In the case of the two-dimensional fluids, the coverage is rapidly no. If the coverage increases a small amount, then the pressure might be should be very large. So this is a very important effect. Of course, this is very elementary, but we remember this effect. So at first, I want to point out at high temperature in equilibrium with the gas phase, hydrogen, absorbed hydrogen is atomic and weakly mobile state, where the absorbed amount is very limited from such a statistical that is called thermodynamic block. Next slide, please. Such a state is briefly or crudely explained by this figure. Of course, this is the potential energy of atomic hydrogen here, the molecular hydrogen, along with the chemical potential. Of course, we can't easily combine. We can't easily combine the chemical potential and electronic potential. So here, at the high vacuum condition, the gas phase and the adsorbed state is non-equilibrium, I say. So that's we have a well-known the potential curve here, but with increasing the temperature and the pressure of the gas phase, we have an increase in the chemical potential, which is equilibrium with the K-soft state, so that the K-soft state becomes very unstable. With some pressure and temperature, the adsorbed state might be transferred to the south surface side. If the iron metal has some capability to accept the subsurface hydrogen, this is the second problem. Would you please return to the previous slide? So the second aspect, yes, thank you, the lower side. So the second point we should consider is the capability of iron surface for subsurface hydrogen under high temperature conditions. First, existence of surface hydrogen is established on several kinds of crystal surfaces such as platinum, palladium, nickel, carbon, and others. Would you please the next slide? Yes, you're right. Thank you very much. And third, the state of hydrogen, the study of the hydrogen enrichment of the iron demonstrated that the hydrogen atoms tend to concentrate around the defective site of the iron lattice. And yes, I have to talk about there is a rafting temperature which is given in the previous film, but I don't want to return. Anyway, there is a rafting temperature. Perhaps some above the rafting temperature, the iron surface becomes automatically or naturally wrapped, which means the defective surface layer is created. In such a surface layer, the hydrogen may concentrate as a subsurface hydrogen. And now, finally, I want to cite the recent embedded atom theory, EML theory, which shows the reason why the potential energy of subsurface hydrogen or palladium 111 becomes lower than that of the hydrogen. There are three reasons, I think. The embedded energy of the hydrogen depends mildly upon the density of the free electrons. There are favorable subsurface sites on palladium 111 where the repulsive image pair potential is low. The third is the repulsive each interaction is reduced by sitting at the subsurface site. Next slide, please. Those three effects are given. This is a calculated result of the embedded atom method. Here we have the absorption side. Here we have subsurface side. With increasing the coverage, subsurface side becomes relatively stable, so that the subsurface hydrogen is realized on the palladium surface. But the similar effect is expected on the iron and other surfaces. Please, next one, please. And here I've mentioned the dependence of the hydrogen embedded energy as the function of electron density. Here the energy will be dependent on the electron density compared with the nickel atom. This is important. And here we have a pair interaction case. With the standard side, the pair interaction becomes lower at the substation. Okay. So finally, I use there exists almost no absorbed hydrogen on the iron surface around 400 degrees C, and about 1 atmospheric pressure for hydrogen gas, but there is alternative hydrogen other. This is a new proposal for the heterogeneous hydrogenation mechanism. Thank you very much.
Thank you so much. There's time for one question.
I would like to address your reasonable postulate, which was in the last section. When we consider a metal like nickel or iron, there are no pieces of evidence that there is subsurface hydrogen in them. You had that evidence for palladium, if I'm not wrong. So why do you postulate that with these metals it must be hydrogen must be first dissolved and that it can attack C?
Okay. We have only the evidence by low temperature and with the high vacuum condition based on the PBS experiment, which is a non-equilibrium with the gas-phase hydrogen. However, our case at high temperature and high pressure of the hydrogen, the surface state is surface condition different. And as I told you, there is a roughing temperature. Above the roughing temperature, the surface becomes naturally rough, and defective size is created under the surface. Such a surface size is favorable for the subsurface hydrogen, which is one of the postulation. And we have ellipsometric evidence. Such a result can be well explained by the present postulation. So this might be supported by other experiments in the near future.
We have time for 2 questions.
Yes, my name is Keus TUS from the Netherlands. For several years, we were studying alexometry of nickel, iron, and copper, and we were using just a helium neon laser beam. We never have seen any effect of hydrogen down to, let's say, some hundreds of degrees. Only the effect of oxygen, and they always could be related very well to the Auger parameters and the other parameters. So apparently, the effect of hydrogen is either strongly related